Now we're going to go on to our second common type of friction, which is kinetic friction. And in this case, kinetic has to do with motion, and so our object is moving, but not moving absolutely. It must be moving in relation to the surface. So again, we care about the fact that there's a surface here, and if that's, say, a truck bed, the object might actually be somehow standing still in relationship to the ground, but if the truck is accelerating underneath of it, such that it is moving with respect to the truck bed, we would care about kinetic friction. So always consider the surface and ask whether your object is moving or still with respect to the surface. So kinetic friction opposes the direction of motion, and this might come in situations where you also have pulling and pushing forces on your object. We don't say that kinetic friction is opposing the tension. In this picture, it happens to be, but what matters is that it is opposing the motion. So in this case, we have a velocity vector that's to the right. Because of that, we have a kinetic friction force that is to the left. So that is actually how we figure this out. We look at the velocity vector, and then we create the kinetic friction vector from that. We don't just necessarily look at our pulling forces or our acceleration. To get kinetic friction, you look at your velocity. Now, the magnitude is fixed. This makes kinetic friction simpler than static friction, and we'll talk next about how to calculate it. But that's it. So we get to calculate a fixed value in this case. The important thing is to recognize what the direction is, and again, use velocity to figure that out. And again, it's velocity with respect to the surface. So when we calculate kinetic friction, again, here we're just dealing with the magnitude because the direction you would find based on the velocity vector. We again have a coefficient, again, Greek letter, lowercase mu, and again, it has a subscript to represent that this is specifically the kinetic friction coefficient. And we again have our normal force, which in the book is going to be written that way. Use whichever notation you find more clear. So this is pretty simple, right? This is a fixed value. This isn't just maximum like it was for static, but there's a couple of tips. So first, make sure you're using the correct coefficient. When I show you later the table of coefficients of friction, the static values and the kinetic values are different, and sometimes students use the wrong one. So you might have a scenario where both of them are given to you in a problem, so choose the right one. The second issue is that in some problems, you might be told that the kinetic frictional coefficient equals the static frictional coefficient. That's fine, that's just a simplification. So the next thing, and this is really big, again, this is one of the other big mistakes that students make, is that you actually need to determine your normal force, right? That's what this is. So actually determine what that is. Don't just assume that it is mg. There are situations where it is. Many problems, your normal force will be equal to mg, but not in every single problem. So please be careful if you have any additional vertical forces acting, normal force is not equal to mg. If you have an object that's on a surface that's at an incline, normal force is not equal to mg. So please don't assume that. That's a place where students, I see them skipping steps, and early on I'm going to try to point out to you, hey, you've skipped a step here, and even though you've gotten to the right answer, it's because later on I know saying normal force equals mg will be an incorrect assumption. So if you start by writing that your frictional force equals mu mg, that is wrong. That is not what the frictional force is. The frictional force is mu times the normal force, and frequently the normal force is mg, but not always. Lastly, recognize when static friction is needed. Again, what's tricky are there are a class of problems where the object is moving, but not with respect to the surface. So always ask, what is the velocity vector relative to the surface? And that is how you determine whether to use kinetic or static friction. So it's not that hard to calculate. It's really just multiplying two things. But the trick comes into actually calculating the normal force and making sure you're correctly identifying when static versus kinetic is needed. So let's talk through a couple of situations to just talk about what the frictional force is and what we know about these scenarios. And in this case, these are all going to be kinetic, since in all cases it is moving. So now the first thing to do is to talk about which direction the velocity vector is. Now, this is a little tricky in that in this case, for instance, where it's a constant speed, you don't necessarily know which way the velocity vector is. It hasn't told you. But you're pushing to the right, and it's on a level surface, so you can probably infer that your velocity vector is to the right, and that's true. Your frictional force is acting to the left. So in all of these cases, you have a velocity vector that is acting to the right. And the reason we know that is because our frictional force is always acting to the left. Now the next thing to notice, this makes sense because it said speeding up, and so acceleration is in the same direction as your velocity vector. And in the slowing down case, your acceleration is in the opposite direction of your velocity vector. So let's relate the pushing force to the kinetic friction force. Now it might look like they're drawn the same size, but keep in mind that these are not free body diagrams. This here is a sketch. So let's draw a free body diagram. In the first situation, we have an acceleration to the right. What that means is that I have a net force to the right. And remember that you don't actually draw that coming from the point particle representing the object, but you draw that off to the side. So we have to actually draw a picture in a way that we get a net force to the right. So now let's do the thing the book recommends, which is basically drawing a circle and identifying what's happening. Well, so I see that there's a push force here and a frictional force here already identified. Well, there's also going to be a normal force because it's on a surface, and there's a gravity force. And that's going to be the case in all of these. So we get to say that my gravitational force is down and my normal force is up, because the normal force is perpendicular to the surface, and I've attempted to draw the normal and the gravitational forces equal in magnitude. Now that's not because it's always true, but in this case there's no net force in the y direction, so my two y component forces must cancel. Now I do my x components. I have my frictional force, which here the reason that it was sub c is because I'm just reusing a picture from the book. So that's kinetic, and that's kinetic, and that's kinetic. So we would say I have my kinetic friction force backwards, and now we have my push force. Now in this case, I don't want to make my push force equal to the kinetic friction force because I know that there's a net force to the right. So my push force actually needs to be bigger, so that now there is a net force to the right. So we can repeat this process for the next picture, where again I'm creating a free body diagram and I say F net equals 0. Why? Because it's at a constant speed. That means acceleration is equal to 0, so using Newton's second law, I know that my net force is 0. I still have my gravitational force downwards. I'm not going to draw my loop again since that's clearly the same for each of these. I have my normal force upwards, which, oops, I'm sorry, this should have been an arrow and not a hat. And now I say that since my net force is 0 in the x direction, my push force and my frictional force must actually be equal in magnitude so that they cancel. So in the final picture, we say that it's slowing down. Now note that there is still a pushing force happening. I can be pushing something and having it slow down, right? Imagine a car that has the engine running. I'm pushing behind it. We're going okay, and then the engine shuts off. Even if I keep pushing, that car might slow down. So once again, we're going to start with my net force, which I know must be to the left because my acceleration vector is to the left. So F net is to the left. I still have gravity, just like the previous two times. And up. And again, here I can use my other notation. It means exactly the same thing. And now we have, again, the relative strength between your kinetic friction and pushing. Pushing is still to the right, but my net force is to the left. So that means that my frictional force needs to be larger than my push. And if I drew, I don't know, it looks like these kinetic friction forces are similar, but if this one is bigger, the only reason that that could happen was if my normal force was bigger or if it was on a different type of surface. So again, these free body diagrams are really important. Don't think about the calculation and getting numerical values as the point of the problem. Remember that most of the physics is actually occurring when you draw these free body diagrams.